Okay, so let's start. So I want to explain. First, I want to finish the proof of the Lefschetz formula, and then I want to explain the strategy for the proof of the last Weil conjecture. Just as a reminder, so let's see what we did last time. So we had some finite group G and an extension of the group of integers by this G, and we denoted by gamma the preimage of natural numbers, and as we discussed last time, it should be defined as the set of integers greater or equal than 0. So then we have gamma is a subgroup of this monoid. And we consider the following situation. We have some ring lambda, which is in our application will be z mod L to the power n z. So we have a module over this group algebra, module P. And so in particular, I have action. So gamma acts on P, in particular G acts on P. And what we are interested in is the following. We want to take coinvariance of G and P. And then, so there is an action of this monoid on coinvariance, right? I have action of gamma on P, so on the coinvariance, I have action of the quotient. And in particular, I can take the trace of the generator of this monoid, which is 1n, right? It's not the identity at all. So I want to express this as sum of traces of elements of gamma acting on P. And so, so if lambda were, say, a field of complex numbers, and P were any finite dimensional representation, then elementary linear algebra shows that this is equal to the sum of conjugacy classes over all. So this is sum. So gamma here runs, the summation is taken over all gamma that go to 1 here. And prime here means that we are taking the sum over the G conjugacy classes here, and we take the trace of this gamma acting on P. Well, and because we sort of, we consider gamma modulo the G conjugacy, I have to divide this by order of the stabilizer, which we denoted by Z gamma, Okay? So this is a trivial statement, and the main observation that we made last time is that you can write this formula so that denominators do not appear. And this will be crucial for our application. So this can be done in the case when, under some extra assumption that P is finite projective over lambda G. That's an extra assumption. And in this case, so here I will put quotation marks because this is really not well defined if this number is not invertible here. But we made sense of this. We rewrote this as we defined some quantities that we called trace Z gamma gamma acting on P, right? And now this denominators go away because the difference between these two numbers is precisely this factor. That was kind of the summary of what we did last time. And there is nothing deep in the proof, but the statement is nice. Okay? So it was the observation that under this assumption, this number is canonically divisible by the order. So now let's prove our main result. So, I will call the statement. So we have a curve over finite field of Q elements. So this is that will be a smooth curve. And C is its base change to the algebraic closure. And we have F0, which is constructible Z mod L to the NZ flat sheaf on C0. So F is it's pullback to C. And this comes with the Frobenius equivariance structure. So we have, because it's pullback, we have sort of descent atom, which is this isomorphism, which I call Frobenius also. Again, this structure comes from the fact that F is the pullback. And then the formula is that, so if we take sum over all rational points of C0 of traces, and here as always I will assume that L is not characteristic of K, which will be P. So I take traces of the Frobenius, this Frobenius, acting on the fibers, geometric fibers over these points. And we want to show that this is equal to the trace of the Frobenius acting on R gamma with compact support of C with coefficients in F. So if homology, this homology with compact support, happened to be flat over Z mod L to the power NZ, it would be just the alternated sum of traces. But in general, it's not the case. And only this quantity makes sense because we proved that this is a perfect object, so it can be represented by a finite complex of free modules over Z mod L to the power NZ. Okay, so that's what we are going to prove. And maybe some notation. So my lambda will be Z mod L to the NZ. Okay. So, proof. So the main tools will be this formula together with the Weil formula for number of fixed points on of endomorphism of a curve that relates these fixed points with trace of this endomorphism on homology with constant coefficients. So we reduce this to the case of constant coefficients. So, okay. So here is, first of all, I want to reduce the proof to the case when F is a local system. And let's, okay, so some more notation. So I want to prove, let's call this expression here T prime. So it depends on my curve, and it depends on the sheaf. And this will be T double prime, C0F. So I want to prove that for all curves, all sheaves, these are the same. So first I reduce to the case of local system. So, and this is not that hard. So I take, suppose I have C0, and suppose I have some open subset. Well, that's a constructible sheaf. F is a constructible sheaf, so over some open subset, it's a local system. And let's denote by, say, Z0, its complement. So this is a finite set of points, C0 minus U0. So this is a closet embedding, I will call it I, and this is G. Then I claim that both sides are additive. So T prime of C0F0 is equal to T prime of U0 F0 restricted to U0. Okay. Plus T prime of, say, C0. I first take my F0, I restrict it to Z0, and then I take I low star of that. That's the first statement, and the same is true here. Okay. So look.
Didn't we convince ourselves at some point that the trace is not additive to short exact sequence?
Well, this is a good question. So it's not additive in the sense that if you have two objects, if you have an exact triangle in derived category of perfect complexes and endomorphism of this exact triangle, then it's not additive. However, we gave a proof that if you start with a short exact sequence of sheaves with an endomorphism, then it's still additive. So the idea was that the exact triangle, of course, a short exact sequence of sheaves. Okay, so let me explain the proof, and I will do a comment on the question. So first statement is obvious because well, it's just true because so here all the stocks vanish outside of Z0, and here only stocks at points of U0 appear. So and here you have all the stocks. So it's true tautologically, right? So what really what requires a proof is the second assertion, and that's why we need all these derived filtered derived categories. So you start with a gamma, well, with the following short exact sequence of sheaves. So you take F0, you restrict it to U0, and then you take J lower sheaf of this. It maps to F, and it maps to its restriction to Z0, and then you take I low star of it. So you have this short exact sequence, and so now so then what was the argument? So it gives an exact triangle. So you can take C, F, you can take R gamma of So if you take R gamma of this with compact support, it's the same as cohomology of C with coefficients of U with coefficients in F restricted to U, and then you have R gamma of I don't even need compact support because it's compact support if you wish, but F restricted to Z, and then you take instead of this. So you have this exact triangle, and it comes with this Frobenius endomorphism acting there. So recall that our first attempt, so what we want to show is additivity. We want to show that the trace here is equal to the sum of the two traces. And I gave an example that in general, for an exact triangle of modius over this guy with an endomorphism, this additivity fails. So that is because, but somehow, nevertheless, we showed that a short exact sequence of sheaves give me an exact triangle which has more structure. For exact triangles coming from short exact sequences of sheaves, this additivity still holds. So we use additivity of traces, and let me I will not recall this proof, which was based on the notion of filtered categories, additivity of traces. So you use additivity of traces for short exact sequence of sheaves. It's not a general statement about exact triangles with endomorphism. And let me explain somehow why, reformulate the argument that we made last time. So imagine that you have like, so these are objects in a abelian category, in derived category of lambda modules over lambda. And every object has an endomorphism. Now, this map is a morphism of objects here, right? Induced, which is compatible, which commutes with this endomorphism in the derived category. So if I give myself a derived category, any derived category, for example, this, I can form a new category whose objects are objects here together with an endomorphism. And morphisms in this category are just morphisms between objects that commute with this endomorphism. So this is not a nice category. So a much nicer category is the following: is the category of modules, derived category of modules over lambda of F. So you have two categories. You can take a derived category, and you can take objects with an endomorphism. On the other hand, you can consider the category of complices of objects with an endomorphism, and then localize it with respect to quasi-isomorphisms. So, this is a nice category. It's a triangulated category. There is a notion of that's a category. So you have notion of a morphism here. You have a notion of an exact triangle. And the proof that I gave actually shows that if you have a short exact sequence, well, an exact triangle of objects here, as opposed to objects here with Frobenius endomorphism, then the statement is true. The additivity holds. So the idea behind the proof was to leave this this exact triangle as an exact, well, kind of an exact, well, from just an exact triangle in this category, the objects here with endomorphism, to this triangulated category. This is possible if you start with an actual short exact sequence of sheaves. So this is new, since this is kind of a drawback of triangulated categories. So if you have a triangulated category, there is no categorical procedure that would define for you a nice category of objects with an endomorphism. A nice procedure means that it would, for example, this category would be equivalent to this, right? In order to define this, you have to go back to abelian categories, right? This abelian category is just the same as the category of lambda modules with endomorphisms, with usual abelian, well, with usual notion of morphism.
You also have a functor in one direction.
Yeah, you have a functor. Well, obvious. So let's denote this category of objects with endomorphisms like this, and then you have a functor, but it's not an equivalence of categories. So if you work with some infinity categories, this would be literally true even on this derived setting. So, as Eluzy pointed out in his interview, so when it was kind of observed that additivity fails in this setting, Deligne came, invented a notion of true exact triangle, which means literally a triangle here. And then he showed how to give a proof of the additivity for short exact sequence of sheaves. So then later Eluzy rewrote this using formalism of filtered categories. Okay? Okay, so using additivity of traces for short exact sequence, we get this statement formula. So good. So that's why we needed. So what I want to erase, maybe I still have to erase this. So in order to prove the result, you need to prove that this is equal to this, and this is equal to this. Let's first prove that this is equal to this. So what is special about these constructible sheaves? That their support is zero-dimensional. They are supported in the zero, which is finite collection of points. So step 2. F0 support dimension of the support of F0 is 0, for example, that sheaf. So you may assume that actually support is just one point. Point X in C0. It's closet point. Okay. So what we have here? So what is the sheaf at one? So you can think of F0 as a sheaf, at one point, a spectrum of. So I have a spectrum of K of X. It's a finite extension of spectrum of K, and it sits inside my C0. Okay, and now let's compute both sides. So what you have? So what is the structure I have? What is the sheaf? F0 is determined by its fiber at the geometric point lying over this. So this guy is just a lambda module with an action of the Galois group, K bar over K of X, right? That's because the residue field, well, it's a sheaf here. Now, what I'm supposed to do, I want to compute R gamma with compact support of, say, C of F. What is this? So my input is a lambda module with a Galois action. What do you get as homology with compact support? So let's unravel our definition. First, we have to take this F0 and pull it back to C. So what will be the support of this F? Yes. So it will be, the support will be this. Right? This is a Cartesian diagram. So I have a sheaf here. I can either go this way or I can go this way. And this is a finite collection of points. So what will be the so imagine that this guy, so it's a free module over lambda. Suppose it has rank R. What is the rank of this guy?
Wait, you don't compute the rank of complex.
Oh, yeah, but it's a sheaf supported at finite number of points. So it has only 0 homology. That's a good point.
R times degree of X.
Very good. R times degree of X, because you have the same kind of sheaf, the same stocks. All the stocks at these points, in this finite number of points, are going to be the same. So you just take the sum of stocks, right? If you compute homology of a sheaf on a curve supported at a finite number of points, it's just this. So, this guy has has action of the Frobenius. So it's actually a representation of the group K bar over K, right? Because everything is defined over K. So this must carry an action. So what is it? So I start with a representation of this group, and the output should be a representation of this larger group. What is this? Induction. Very good. So you just induce this guy, F0, of X from this subgroup. So it's a Galois group of K bar over K of X, and you induce to larger group. So as a lambda module, this is sum of these guys over points here, over geometric points lying over X. So, and in particular, well, I have here my Frobenius, so I will rather call it the geometric Frobenius is inverse to arithmetic one, which is generator of this. And in particular, I have its action here. Right? On this induced representation. So what is the trace? So we are interested here. We are interested in the trace of this Frobenius, which is generator of this group, on the induced representation. What is this trace? So suppose you have a representation of, you have following situation. You have a group, cyclic group, well, sort of generated by one element, topologically at least, and this is a subgroup, finite index subgroup, right? And so you induce the representation, and then you take the trace of the generator. What's going to be? Zero, right? Because the Frobenius permutes the factors. So you just don't have the diagonal entries. So it's going to be the trace of the Frobenius on R gamma with compact support of my F is either 0 if K of X is not K, right? But of course, it's not 0 when K of X is actually K, right? Because then you only have, then this induction gives me nothing. It's just recover this, right? The original representation, and it has action of the geometric Frobenius, and that's what I get. So the trace of f x acting on this fiber, right? Good. So now if you compare this with this formula, that's precisely what you have. So only rational points contribute, right? And so every rational point contributes precisely with this. So this at least, it proves the formula in the case when my f is supported with a finite number of points. So that means that we have this, this equality. That's good. So it remains to prove this. So I can choose U0 so small now that this is a local system. So we already reduced to the case of local system. So step 3, which is really the key step, is so we are in the following situation. So we have C0, which is affine. I may assume that it's affine curve. Smooth affine. F0, a local system. So that's given by a representation of the fundamental group of this curve. And what else? And I may also assume that C0 of K, C0 has no rational points. Right? So because I can add them to Z0. So in this case, the left-hand side of the formula is 0 tautologically, because this set is empty. So what we want to prove is that, in this case, that T double prime is equal to 0. Okay. So let's start proving this. So we have C0, and we know that, so we have a local system with finite coefficients, right? It's a representation of the fundamental group, and it necessarily factors through a finite quotient, right? Because the group of automorphism of a finite lambda module is finite. So that means that we can construct a Galois cover F. This is connected. Okay, maybe I'll write it here. So connected Galois cover. And so I will denote the group, the Galois group G. In text here, it's the quotient of the fundamental group of C0. And so it has a property that if I pull back my local system to this cover, is actually constant. So that means that it's a constant sheaf with some coefficients m. And so what is m? So if I already know that this sheaf is constant on a connected scheme, then so this m can be recovered as simply global sections. So m is canonically global sections on S0 of F inverse of F0. Right? So let's use this. Okay. So I have. So what is the extra structure I have? So I start with a sheaf on C0. I pull it back here. This is a G torsor. So what I get here is a sheaf. Well, it's a constant, but it has an additional structure. It's equivariant with respect to this G action, right? Its fiber over point X is the same as the fiber over point G of X because it's pullback. So that means that this is equivariant sheaf. In particular, it gives me an action of G here, right? So G acts here. So the local system on C0 can be recovered from this constant sheaf together with this G action. That's the descent data. So namely, how it can be recovered. So I want to look at the direct image of this. So there are two ways to recover it. So either you can map F0 here and then take G invariance, or you can use a trace map. There is this trace map. Remember that, well, that's a finite entalmorphism. So F low star is the same as F lower 6. So by adjunction, you have the trace map to F0. Okay? So now this sheaf was equivariant. So in particular, it means that you have action of G here. So, and this map actually factors through G invariance. Yeah? Because there is no action of G here. And I claim that this is an isomorphism. And this is obvious because you just check it in stocks. You take any stock over a geometric point, and then the stock of this, the stock of this guy will be sort of G times G copies of the stock of F0. G acts transitively on the summons. The trace map is the summation map. And so you get an isomorphism on stocks. So very good. So F0, that's kind of a way of phrasing the category of sheaves on C0, local systems of C0, which become trivial when you pull them back, is equivalent to the category of G modules, right? That's something that we already know. G is the quotient of the fundamental group. So, and explicitly you do this. But now I want to use the projection formula, right? That's a constant sheaf. So let's say that we take, we write this. So you take a direct image of a constant sheaf. So this is the same as taking direct image of lambda, right? And then you tensor it with M. So direct image of lambda has an action of G. This also has an action of G. So this has diagonal action. This is just a lambda module, right? It's direct sum of few copies of lambda. So that's this sheaf by easy version of the projection formula. So, and I have this expression. That's my F0. Okay? So you see now where the coinvariants appear. That was, so now let's do the computation. Okay, so so we are interested actually not in F0, but we want to take the homology with compact support. So I have C0. Yeah, so now I will draw a diagram for you. So here I have C0. Here I have S0. This is a Galois cover. So I can choose a smooth compactification of this curve. And I can also choose a smooth compactification. It's unique, right? It's normalization of C0 bar here. And this is S0. So I arrive to the following situation where these are smooth projective curves, smooth projective. This map need no longer be a Galois cover, right? It could be ramified away from this C0. Okay? So, but still, because C0, this curve is constructed functorially, right, as normalization, you have action of G here. Now let's do the computation. So let's compute R gamma of C with coefficients in F. And I want to use this formula. So that is how I want to write it. So I take R gamma with compact support of C with coefficients in F rho star of constant sheaf. Yes. Now I need to tensor it with M. Over lambda. And here I need to take, well, that's a complex. Yeah, this is not necessarily, well, yeah, that's okay. So M is definitely free module over lambda. So it's, because it's invariance in stock. So, but let's just for safety, because this is a complex, put here L. But in fact, it's free, so it's you can compute the standard product term-wise. Now this gives me this, and now I need to take coinvariance. So I tensor it with lambda over lambda of g. That's derived coinvariance, right? So what I'm using here, I have a sheaf with action of g, and I'm interested in R gamma of that sheaf. And I claim that it commutes, and then, well, I'm interested in R gamma of this sheaf of coinvariance. I take the claim that taking derived coinvariance commute with R gamma. How to check this? Just choose for M a projective resolution, and then apply. So if M were a free module, right? If M were just lambda of g, this the commutation property with G invariant would be obvious, because multiplying by a free module and then taking G invariant means just nothing. So therefore, if you work in derived category, this formula is true for any M. So we want to compute the trace of the Frobenius acting here. Okay? So let's do one more observation. So let's take, let's observe, so here I have the homology of C with coefficients in direct image. So this will be L, well, lambda, coinvariance. And here I replace this by R gamma with compact support of this. S, and this coefficients in lambda. Tensor it with M. Good. So we kind of express the quantity where we want to compute the trace in terms of homology of a smooth curve with constant coefficients, but consider it as a G module, right? I need the action of G, remember action of G here. So this is a G module. I tensor it with M. I take the diagonal action of G, and I take coinvariance, derived coinvariance. And we want to compute the trace. So let's call this object P. That's a complex. It's a complex of G modules. So I claim that this P, so that's an object of the derived category of modules over lambda of G. But I claim that this is perfect. And remember that perfectness means that it's a quasi-isomorphic to a finite complex of free module, of projective modules over this group algebra. Why it's perfect? Because we had a criteria for perfectness. So in order to show that this is perfect, we have to check that homology supported in finitely many degrees, they are finite over this guy. And also we have to show finiteness of Tor dimension, right? What does it mean, finiteness of Tor dimension? It means that if you tensor it with any n and take coinvariance, derived coinvariance, then you get homology only in finitely many degrees, right? So I claim that this P has finite Tor dimension. Okay, so what this explicitly means is that if you take P and you tensor it with N, and, well, you take the derived tensor product, so over C over lambda of G, well, then I claim that homology actually vanish is negative degrees. And why that? Because what is this? It's the same as first taking this guy, tensoring it with some n, consider it as a G module with diagonal action, and then take derived coinvariance. But we already know that this derived coinvariance compute homology of M tensor N, and homology supported in non-negative degrees. So we have this vanish. That's called the finiteness of third dimension, and we have a criteria of perfectness of a complex of modules over any Noetherian ring. So this is applied here. So why is that good? Because so that means that this P dot is represented by a finite projective complex of G modules. And so now I have, in addition to this action of G here, I have the action of the Frobenius, right? Of the geometric Frobenius. It acts on everything, so it acts on my P. So P is a G module together with action of F, and as a G module, it's complex of finite projective. So you may think of P dot as a complex, really as a complex of finite projective, and term-wise on this complex you have, on each term of this complex, you have action of F, which commutes with the differential, right? Because the derived category is, equivalent to the category of, homotopic category of complexes of projective modules, right? So now we are in a position to apply our trace formalism. Let's see here. So I need a monoid extension. And for the monoid extension, well, F commutes with G. So I just take gamma be the trivial monoid, G times N, right? And gamma acts on P. And, well, G acts here, and 1 N acts by Frobenius. Okay? So, so now I apply the formula for the traces on coinvariance. So this this is precisely 1, right? And I need its action on R gamma of C with coefficients in F. And we have this expression. It's coinvariance. So therefore, it's equal to the sum over all gamma mapping to 1. So all elements in here whose second coordinate is 1 up to conjugation by elements of G. So this is essentially sum of the conjugacy classes of G. And you take this funny trace. Z gamma in this case is just the centralizer. Well, if you identify these gammas with elements of G, this Z gamma will be the centralizer of your element. So, and you take the trace of gamma acting on R gamma C of well, where? I will write it down. So on this guy. So R gamma with compact support of S with coefficients here, tensored with M over lambda. Okay? So let's see what it is explicitly. So that's sum. So, well, these gammas here that map into 1 and 1-to-1 correspondence with G, right? So I actually take sum over conjugacy classes in G. So, and I need to compute the trace of gamma. How gamma acts? Well, it's action of the following element. It's G inverse times F star. So I look at the action of R gamma, C lambda tensored with M. That's action of my gamma. Yeah, and here I have a centralizer. That's the centralizer of the group of all elements that commutes with G. All right? So, well, that's because gamma is what? Is action of G composed with action of the geometric Frobenius. If you want really G act, you need to put inverse here. So otherwise, it's not an action. So now, so here I take the trace of product, well, on a trace of a endomorphism on a tensor product of two representations, right? The tensor trace of the tensor product is equal to the product of traces, and we had the formula, this refined formula. So with, I can rewrite this. It's sum over conjugacy classes again, G and joint. Yeah, so here maybe prime is already taken care of when I write. So, and I take this trace ZG. So this is G inverse F star acting on R gamma with compact support with trivial coefficients. And I need to multiply it by the trace on M. So this times the trace of this guy acting on M. But F does not act on M, only G acts on M. So that will be the trace of G inverse acting on M. Okay, and no ZG appears here. So I take sum over all these guys, over all conjugacy classes of these expressions. Now what we want to prove? We want to prove that the sum, this is our T double prime, right? We want to show that the T double prime is 0. If you want to prove that sum of several quantities is 0, it suffices to prove that each quantity is 0. And that's what we will prove. So enough to show that this first term, this for any G in G, the trace G inverse F acting on homology with compact support of S lambda is 0. That's because we assume that C0 has no rational point, so this term is obviously 0, so that's what we want to prove. Okay, so that's very good because now F does not appear in this formula, the sheaf, right? It's a statement about homology with constant coefficients. And we are in position to apply Weil's formula. So, okay. So here is one more simplification. So here I have this sophisticated trace, but I claim that it's enough to prove this after multiplying by the order of this. So remember that. So I claim that. So what is lambda? Lambda is z mod a to the power nz. So n here can be any number, right? Let's increase this n so that so if this group, order of this group, is relatively prime to L, then proving that this statement is equivalent to proving that this number multiplied by the order of this group is 0, of course. But otherwise, I claim that I can replace this by some larger z take A to the power n z, where n is very, very big. And then I want to show that even modulo L to the power of this large n, this trace, already usual trace, acting here on the same guy as this is 0. So why that? So if I can prove this, then I can also prove this. So I know that this number, which is an element here, is equal to 0. So this integer is equal to 0 modulo L to the power n. So that means that the original, if I reduce this guy modulo smaller power of n, it will be 0.
Then we need some base change property for traces.
Yeah. So if you have a module which is projective over this guy, and you take its trace of an endomorphism, then that's one thing you can do, and then reduce it. So you get an element in this ring, then you reduce it modulo smaller power, and that's the same as first taking the reduction of your module, modulo smaller power, and then take the trace. It's property of matrices. So that's what we are proving. And so again, using the оно не взаимно просто. Но смотри, вот мы хотим доказать, что вот нам достаточно доказать, что вот такое вот выражение, вот это вот выражение, вот да, и вот это, что оно равняется нулю по модулю вот этой степени L. Но это то же самое, что если я его умножу на какое-то фиксированное число, вот это, и докажу, что... прости, пожалуйста, мы хотим доказать, что вот это число, вот это, которое выделено, что оно равняется нулю по модулю вот этой степени L. Но это то же самое, что сделать следующее. Умножить это число на порядок z, который фиксированное число, и доказать, что результат равен нулю по модулю большей степени L.
Ну, в смысле, что предположим, что она не равна нулю, да, можем, да?
Да,
Что...
да, ровно так.
Ну, просто вот, ага, ну, хорошо.
Ну, например, допустим, что порядок вот этого равен L. Тогда надо просто вот это n большое взять равным n плюс 1.
Я понял, просто форма, в которой ты сказал, сначала не было.
Нет, ну, прости.
Я же хотел уточнить, что...
Ага, да.
Спасибо.
Okay. So, now let's use, first we use additivity. So again, this is homology with compact support of constant sheaf on a non-compact curve, but I want to write this trace of G inverse F star acting on R gamma with compact support of as sum of two traces. That's, well, of difference, better say, of two traces. So first I take the trace of the same operator, since it acts on, so I consider the compactified curve, right? And on this compactified curve, I still have action of G, because compactification is functorial, and I need to subtract the trace of this so here I have G inverse F star acting on just homology of constant sheaf, but supported so I take ILO star of lambda S bar minus S. And here notation is that I have S, I have S bar, and I have the embedding of S bar minus S. And this is my I. Right? So this is a very simple sheaf. It's supported at a finite number of points, constant sheaf, and I take the trace of the Frobenius. So what is the homology of a constant sheaf supported at a finite number of points? That's just a free abelian group generated by these points. So what is the trace of, well, now let's write everything down. So we compute the first trace using Lefschetz formula. So this will be Weil's formula. So this will be the number of fixed points. So I take this, and I take G inverse F, and I take its K bar points. That's the cardinality. What? No, K bar points. So there is no K anymore. So the Weil's formula is geometric. So you have a curve over an algebraically closed field, and you have its endomorphism, and you compute the number of intersection of the graph of this endomorphism with the diagonal. In this case, G is an automorphism. F has zero differential, so the diagonal intersects transversely the graph of this. So this is just the usual, well, set theoretically. And now let's compute also this. So we already, so you subtract simply the number, the same quantity. For zero-dimensional varieties, it's an obvious statement. So you take G inverse F. So this is a finite collection of points. You take only those points which are fixed under this. Because, again, that's a permutational module. And you Okay. So we reduce to proving that this quantity is 0. And now I need your help. So what does it mean? It means that any point here, which is invariant under this, actually lives here. So this is C bar, right? So any point here which is invariant under this endomorphism lives over C.
Because the morphism should be ramified at that point.
Well, because G acts here, trivially here, right?
The fibers over
Yes.
0.
So you have G inverse F here, and so it's over F, because action of G here is trivial. So if you have a point here which is fixed under this, it goes to a point here which is fixed under the Frobenius. But we assume that C has no rational points. So there are no points fixed under the Frobenius. So this quantity is 0. And this completes the proof. Okay. So I want to use 7 minutes to kind of explain a strategy for the proof.
Сейчас такой вопрос. Ну вот это решение гамма было нужно нам только в виде прямого произведения.
Да, только в виде прямого произведения. Но там вот в прошлый раз мы какое-то другое применение. Да, здесь только в виде прямого произведения.
Ну вот гамма.
Да.
Don't we need to explain how do
В прошлый раз мы нигде не использовали.
Нет.
How do you relate the L-adic Laffer's formula, which has QL coefficients, with something that has coefficients modulo L to the n? You have to somehow explain why our matrices have integer coefficients. Why this is.
Well, well, at the end, any constructible sheaf, QL sheaf, is by definition comes from ZL sheaf, in the sense that the category of QL sheaves is the tensor product of ZL sheaves. So you take the same objects and morphisms get tensored with QL. So in the statement in a logic statement with QL coefficients, you may assume that your sheaf is actually a ZL sheaf. There is absolutely no difference. Only morphisms are different, but not the objects. QL sheaves is the category of QL sheaves is the tensor product of the category of ZL sheaves with QL. That's a very good point. So, for example, any QL local system is normal variety, is a continuous representation in QL vector space, and continuity means that you have invariant ZL lattice. Compact group preserves the lattice. Okay, so let's kind of see where we are. So we proved Lefschetz formula with finite coefficients for curves, and I already explained that it implies the Lefschetz formula with QL coefficients, even with finite coefficients for every scheme. The statement holds with finite coefficients. Use just proper base change. And so we we have as a corollary, we have a formula, Lefschetz formula with QL coefficients on any scheme and with any QL sheaf, with coefficients in any QL sheaf, and in particular with constant coefficients. And as a corollary, we have a formula for the L function, for zeta function. So suppose we have x0 is any scheme of finite type over FQ. So we have zeta function, just usual zeta function we started this course with. So it's product of over all points, closed points, in x0 of 1 over 1 minus, so it's counting sort of function. You count points. Every point comes with a weight, and its weight is 1 over t to the power degree of f, degree of x, right? That's the definition of zeta function. And so what we proved is that for any scheme, this zeta function is equal to the product over all over I equal to 0 twice dimension of x, twice. You take the trace, oh sorry, not the trace, but the determinant of the characteristic polynomial 1 minus Frobenius times t acting on homology of this compact support of x. X is the base change with QA coefficients. Okay? And you need to take it to the power minus 1 to the power I plus 1. So this is a trace characteristic polynomial. Well, it's a version of characteristic polynomial of, right, because you put c not here, not here. So of an endomorphism acting in a finite dimensional vector space. And so it has the following, so if you see that zero homology comes with negative sign, so you have product P1 of t, P3 of t, P so on. Let's put some dots here and divide finitely many polynomials, divide by P0 of t, P2 of t, and so on. So this Pi are these characteristic polynomials. So that's what we proved. And particularly that's a rational function. But now, so I want to recall the statement of the last Weil conjecture. That has QL coefficients. Very good. Yes. So that's a very good point. So on the one hand, what is written here is a power series, actually with formal power series, actually with integral coefficients. But this Pi a priori are polynomials with QL coefficients. Well, of course, integers is a subring, so the statement makes sense. But now, what we want,
But you explained that actually it has ZA coefficients.
it has ZA coefficients, right? But still, it's not a priori clear that they are actually integers. So what we want is that, so if x0 is smooth projective, so for the statement, for this statement, we don't need this. And alpha, say Pi of alpha is 0, so alpha is a root. Or maybe let me write it here because I need some space. is 0, then absolute value of alpha is equal to q, right? Q is this negative I over 2, right? So first of all, what it means. So alpha, this is a polynomial with QL coefficients, maybe with ZL coefficients. Alpha is its root, so it's an element of algebraic closure of QL. So what does it mean to take this norm? Well, you can take the L-adic norm, but that's not what is meant here. So instead, we look at QL bar, and we look at all embeddings. Well, that's an algebraically closed field whose cardinality is equal to the cardinality of the field of complex numbers. So you can always embed it. In fact, they are isomorphic. But so you can take any embedding. OK, so maybe C. So what I really mean here is that you take for any embedding, that's for any C. This number, the absolute value of this complex number is equal to this. If you think a little bit, if I give myself an element here such that for all embeddings, its absolute value is equal to something, this is only possible if this number is algebraic over Q. Otherwise, I can send it to any element I want, right? If it's not algebraic. And then extend it. So implicitly here, we mean, well, at least, so this kind of implies that this polynomial has coefficients at least in Q bar. But in fact, it is true that this coefficient has rational. This polynomial has rational and even integral coefficients. Right? So still you have, so then alpha is an algebraic number. Still you have many embeddings of this algebraic number. Well, you have many conjugates, right? So, but maybe, yeah. So they're all roots of the same polynomial. So if you know this for all alpha, then it's OK. So that's what you want to prove. And so what is the difficulty here? So the difficulty is that, first of all, so we succeeded in proving, well, we proved many results on L-adic homology, but all the proofs were based on reduction mod parallel of A. And that's the only technique that we have, right? Because the homology, L-adic homology, is defined first with finite coefficients and then passing to the limit. And so even if you know something about the reduction of alpha modulo L to the power n, it doesn't tell you anything about its complex eigenvalues, its complex absolute values, right? Complex, if you know a rational number, if you know it modulo arbitrary large power of L, it doesn't tell you anything about its absolute, kind of real absolute value. So, so there must be some kind of completely new insight. That's why it's difficult. So I will explain a proof of this. And so, so the proof is, all the proofs are based on the following. They are not kind of, Grothendieck didn't like it, these proofs. So what you do, you put your x0 in families. So I will illustrate this first in the case of hypersurfaces. In the end, any variety is birational to a hypersurface, so you may expect that it's enough to prove the theorem only for hypersurfaces using some induction on the dimension, and that's true. And hypersurfaces can be deformed. It's easy to deform. Hypersurfaces are parameterized by polynomials of homogeneous polynomials of some degree in projective space. So you have a modular space of all these polynomials for which the corresponding hypersurface is non-singular, right? You remove the discriminant. It's just the open subset of the affine space. And this is kind of, you think of this as a universal hypersurface. And so the strategy will be the following, that we will prove explicitly by direct computation, it's due to Gauss, for one particular hypersurface. For example, for for Fermat surface, sum of div powers of the coordinates equal to 0. Just for one hypersurface, we compute explicitly the number of points and compute the zeta function. And we'll check that it's true. And then we will study, we'll show that we'll look at this morphism, and we'll consider not just homology groups of fibers, but this homology group of fibers, by proper base change theorem, they are stocks of f log chic Ri of constant sheaf. So if you compute this stock, it's the same as homology with compact support of member of this with QL coefficients. So you have so all this kind of the number of points on all hypersurfaces are controlled by this Lefschetz formula and proper base change by these sheaves. These sheaves live over an open subset of affine space. And then we reduce the statement to the following. We have some sheaf, which will happen to be a local system, so also a representation of the fundamental group of this S, for which, such that for one fiber, this assertion is known. The statement about eigenvalues of the Frobenius acting on the stock. And then we'll show that it's automatically true for all other stocks, for instance. Okay? So at the end, the proof will be reduced to kind of a statement about representation of the fundamental group of this S. And, so if you think of S as, again, it's an open subset of affine space. So you can actually even make, you can connect any 2 points here by a rational curve. So we will reduce it to the case when S is an open subset of P1. It's a rational curve. So we will have a local system on P1, on open subset of P1, such that for one fiber, this assertion is known, and then we'll show that it's true for all others. So it requires, so that will be the strategy that we will realize. Next time. Нет, как гиперповерхностность, я ничего не говорил. Там как бы, по сути дела, надо как бы использовать, что любая, значит, вообще, вот Делинь в своем интервью пишет, что как бы он, используя... Это не пучок Лефшица, это просто семейство гиперповерхностей. Гораздо более простая вещь. Всех, да? Да, всех. Вот, но, причем я только не особых, прости, пожалуйста. S это открытое подмножество. Я хочу сначала как бы для гиперповерхностей доказать, а потом, значит, общий случай, как он будет выводиться? Мы там возьмем гиперповерхность, которая бирациональна нашему многообразию, мы там разрешим особенности, чтобы она была не особой, мы... Типа того, да. Да, это теорема о примитивном элементе.
Ну, я так.
Вот. Но там есть какие-то технические детали, но как пишет Делинь, в тот момент, когда он доказал это для поверхностей, остальное было делом техники. Вот.
Да, теперь я понял, да.
Окей. Well.
Take a formula for the zeta function. And it is a formula, but it's not kind of obvious. Is there an actual way to compute all these characteristic polynomials, for example, by a computer program, either by developing the theory of homology further or by using methods?
Well, the only way. So what do you mean compute this? What you can do, you can kind of find an estimate for dimension of these guys. So then a polynomial, right? So if you know that, for example, if you have an elliptic curve, say, then you know that you have only h0, h1, and h2. So h0 and h2 are easy to compute. So you have h1 with the action of Frobenius. So that's a two-dimensional vector space with an action of the Frobenius. And you need to compute the characteristic polynomial of this Frobenius. So that means that you need to compute two numbers, right? Eliadic numbers, which happen to be integers. So how you can compute this? Well, if I give you an equation of an elliptic curve, then so the only way to compute it is calculate the number of points over fp, maybe over fp squared, if you are stupid enough. So if fp in fact is enough because you also know the top coefficient of the determinant of the Frobenius, it's equal to p. So the Lefschetz formula tells you that if you know the number of points on varieties, so if you have a variety here, and if you know the number of points, or fq points, maybe fq squared points, finite over some finite collection of finite set of finite extension of this guy, then you know everything. Because then you just plug it in Lefschetz formula, you get equation for the coefficients, system of linear equations.
Yeah, so this works if E is small, but even that, if, for example, I have some surface in P4, which is not a complete intersection, I don't know how to lift it to characteristic 0, how do I even know beta numbers?
Yes, so if you can't lift it to characteristic 0, then I think you are in troubles.
It can become like some a priori bounds at any surface which is given by two equations of degree 10 can have beta numbers.
Well, if it's complete intersection, then the answer is very simple. No. Well, first of all, right. If it's complete intersection, you can always lift it over C. Another way of doing this is that for complete intersection, only the middle homology group is interesting. Otherwise, all other groups are trivial. And so it amounts to computing Euler characteristic. And how you compute Euler characteristic of a algebraic variety? You project it to Pn and look at the ramification divisor.
But is this true that, for example, for complete intersections, the beta numbers are large? So it can be like some a priori bounds.
Well, so there's a question over complex numbers, right? So can you express?
I'm not sure that the answer is the same over complex numbers, for example.
No, that is the same. So I will maybe even next week I will start prove it. We'll maybe even prove the smooth base change theorem, which will explain that, which will imply that if I have a variety over fp and it's liftable over to a smooth projective variety over ZP, then a Tal homology over QP bar have the same cardinality as a Tal homology over FP bar. So,
I mean, if I study all, let's say, all projective varieties which can be embedded as surfaces of degree at most 10 at P4, some of them are not completely
oh, then I don't know what to do. So if it's not liftable, then I don't know. So, but though, right, maybe still you can do something. You can kind of catch H1 by intersecting with taking a hyperplane section. So you get a curve, and it's known that H1 is embedded in the homology of this curve. So if you can bound the dimension of a hyperplane section, you can bound H1, and then you need to compute only H2, and maybe you can do something with the Ehlers-Danlos.